In 1953, a Comet pressure cabin test section reached roughly 18,000 applications of normal working pressure. Engineers treated that result as evidence of a long structural life. 4 months later, a production Comet broke apart over the Mediterranean after 1,290 pressurized flights. The aircraft had met its proof requirements, and the specimen had survived far more cycles than the aircraft. Somewhere between the rig and airline service, a reassuring number had lost its meaning. On January 10, 1954, BOAC Flight 781 left Rome for London. G-ALYP climbed normally and sent a routine position report over the Italian coast. At about 27,000 feet, its final radio transmission ended with catastrophic suddenness. Wreckage fell into the sea near Elba. All 29 passengers and 6 crew members died. The aircraft was the first jet airliner in scheduled passenger service. It flew higher and faster than the piston transports it replaced, inside a cabin pressurized more heavily than common civil practice. The loss raised an immediate question about engines, fuel, controls, weather, and structure. The answer later became famous as a story about square windows. That shorthand misses the opening where the failure was actually found and the test assumption that allowed it to develop. The Court of Inquiry found that fatigue caused the pressure cabin of G-ALYP to fail in the region of a rear aerial window on top of the fuselage. It judged one countersunk bolt hole the most probable local origin, while leaving the exact first point unresolved. Repeated pressure, concentrated stress, and local construction details explained the fracture. The harder question was why the test program had not exposed that weakness before passengers entered service. How could an aircraft exceed the accepted strength requirements, survive an apparently punishing test, and still fail in ordinary airline service? Solving that required a second disaster, a full airliner submerged inside a water tank, and enough wreckage raised from the Mediterranean to rebuild the first few milliseconds of breakup. The investigation would change how a new aircraft proves that its cabin can survive a lifetime. De Havilland began the Comet project in 1946, before any prototype had flown and before civil aviation had much experience with a large jet pressure cabin. The first prototype took off in July 1949. Scheduled BOAC service began in May 1952. 4 jet engines were buried in the wing roots, leaving a clean silhouette and a cabin quieter than the piston transports passengers knew. Routes that had required a sequence of slower legs could be flown at greater speed above much of the weather. The Comet made the future of airline travel physically convincing before the structure had accumulated enough years to reveal its fatigue behavior. Well, high altitude created the Comet's advantage and its structural demand. Outside, air pressure fell as the aircraft climbed. Inside, the cabin remained dense enough for passengers to breathe comfortably. The shell had to contain that difference across its skin, frames, joints, doors, windows, aerial openings, and every fastener connecting them. The Comet's normal differential pressure was about 8.25 pounds per square inch, roughly 50% higher than values than generally used. 8 pounds sounds small when applied to 1 inch. Across thousands of square inches, it becomes a large force trying to expand the entire fuselage. Frames and skin carry that load around every opening. The load also repeated. On every climb, the pressure difference rose. On descent, it returned towards zero. A shell can survive one large load and still accumulate damage under thousands of smaller cycles. Microscopic slip at a highly stressed detail can form a crack. Each later cycle opens the crack slightly farther until the remaining material can no longer carry the cabin load. Fatigue was not unknown in 1954. Aircraft designers already considered repeated wing and engine loads. The difficult part was predicting the life of a new pressure cabin with few years of service evidence. Requirements emphasized static strength and proof pressure. Repeated load rules for cabins were still developing after the Comet design was largely complete. A smooth cylinder spreads pressure stress around its surface. A door or window interrupts that path. The load has to flow around the opening, which raises stress near corners and edges. A fastener hole can raise it again at a much smaller scale. Shape, thickness, joint design, countersinking, and workmanship all influence where that local peak appears. This is where the square window story becomes misleading. G-ALYP's first cabin fracture was traced to the region of a rear ADF aerial window on the roof, not to an ordinary passenger window. The court treated high stress around cutouts and sharper stress at local construction details as the fundamental problem. Visible outline was one part of a layered structure. Before the aircraft entered service, de Havilland exceeded the one-time static requirement. The cabin was designed for 2.5 times working pressure and tested to twice working pressure. Surviving that load showed that the structure could contain a large pressure once. It did not determine how a production cabin would respond after many ordinary flights. The repeated load evidence appeared stronger. The specimen represented the forward portion of the pressure cabin rather than a complete aircraft. Engineers closed its cut ends with heavy test bulkheads, applied high-proof pressures, and later cycled it at normal working pressure. By September 1953, it had accumulated about 18,000 applications of P in total, including roughly 16,000 in the later program, plus earlier loads above working pressure. The structure in the rig looked like a piece of a comet, and it had survived an amount of cycling that seemed to place normal airline service far inside a safe life. G-ALYP left Rome at 9:31 on the morning of January 10th. The route carried it northwest toward Britain with 29 passengers and 6 crew. At 9:50, the crew reported over Orbitello Beacon. The flight was near 27,000 feet. Climbing and weather, the inquiry later found, had not contributed to the loss. The last communication belonged to an ordinary handoff between stations. Nothing in the record described a warning, an emergency checklist, or a prolonged struggle before the transmission stopped. The final message ended in the middle of normal communication. Witnesses saw pieces descending near Elba, including a burning part. The fire did not establish that an onboard explosion began the sequence. At altitude, a pressure cabin rupture could separate structure, systems, fuel, and electrical sources within moments. The sea received the evidence across a wide area. BOAC suspended normal Comet passenger service the next day. Aircraft that had represented speed and national technical confidence now stood idle while crews, engineers, and passengers waited for an explanation. The suspension was voluntary. The government had not yet withdrawn the aircraft's certificates of airworthiness, and the cause remained open. Investigators considered fuel, engines, flight controls, turbulence, structural overload, and explosive decompression. A fuel system correction would not repair a pressure shell, and a structural modification would not solve a control failure. Each theory pointed toward a different fleet response. The Mediterranean made recovery slow and selective. Search teams mapped where wreckage had fallen and raised pieces that could be located. Early evidence was incomplete. The aircraft had broken into many sections, and damage from the breakup, sea impact, and recovery could be confused with damage that began the accident. Investigators needed to determine which structure failed first. The first investigation produced a broad modification program. Components were inspected, possible fuel system hazards were examined, and suspected control and engine problems received attention. De Havilland, BOAC, the Air Registration Board, and government advisors were working from an incomplete field of Mediterranean wreckage. No fracture sequence had yet isolated the cabin as the first structure to fail. Against that uncertainty stood a concrete laboratory result. A cabin section had endured thousands more pressure applications than any service Comet. The result did not prove that fatigue was impossible, but it made fatigue a less persuasive explanation than it would become after Naples. Officials had to decide whether the inspected and modified fleet could return while the Elba cause remained open. Continuing the suspension carried consequences for BOAC, de Havilland, passengers, and Britain's jet program, but the record does not support a story of officials knowingly accepting a fatigue defect. Their modifications addressed the mechanisms then considered plausible, and the existing cabin tests still suggested substantial life. After technical advice and ministerial consideration, passenger service resumed on March 23rd. The decision was an attempt to manage uncertainty, not a declaration that Elba had been solved. On April 8th, 16 days after service resumed, G-ALYP left Rome for Cairo. BOAC owned the aircraft, and South African Airways operated it under charter with a South African Airways crew. Near the top of its climb, around 35,000 feet, it was lost near Naples. 14 passengers and 7 crew members died. A small inspection panel issue found before departure had been corrected, and the inquiry found it did not contribute. The second loss changed the standard of proof required for continued operation. BOAC suspended the fleet again, and on April 12th, the type's certificates of airworthiness were withdrawn. 2 aircraft had now disappeared near the top of climb within 3 months. That resemblance was strong enough to end passenger service, but resemblance alone could not establish one technical cause. The available evidence was unequal. G-ALYP lay in water too deep for the recovery achieved off Elba, leaving the second accident with a similar outline and far less physical detail. That difference would remain important even after the inquiry. Enough of G-ALYP was recovered to support a positive fatigue finding. Too little of G-ALYP came back for investigators to prove the same fracture or an exact origin. The court would say only that the Elba explanation appeared applicable to Naples. A third earlier Comet loss also had to remain separate. G-ALYP broke up near Calcutta in May 1953 after entering a severe thundersquall. The Indian inquiry attributed that accident to structural overstress from severe gusts or pilot overcontrol and loss of control. The 1955 court found no sufficient reason to overturn it. Similar wreckage did not automatically mean an identical initiating cause. After Naples, the Minister of Supply directed the Royal Aircraft Establishment at Farnborough to use its full resources. The program combined flight trials, structural tests, fatigue work, fuel system investigation, model drops, wreckage reconstruction, and repeated pressurization of a complete Comet. The inquiry would not rely on one dramatic clue. The central experiment used G-ALYP, an aircraft that had already completed 1,230 pressurized flights. Investigators would reproduce more flights on the ground, watching a complete production fuselage instead of a partial section. They also had to ensure that when it failed, the pressure release did not destroy the very crack they needed to examine. The RAE placed G-ALYP in a large tank and filled the cabin and surrounding space with water. The test kept the complete fuselage, doors, windows, aerial openings, frames, and joints in their production relationship. Water stores far less destructive energy than compressed air at the same pressure. If the shell opened, pressure would fall without the blast that could tear neighboring evidence into secondary damage. Engineers could stop the pumps, drain the tank, and approach the fracture with its earliest region still physically connected to the rest of the aircraft. Hydraulic equipment raised and lowered cabin pressure to represent one climb and descent after another. Separate loads bent the wings to approximate normal gust forces, so the pressure shell did not sit inside a completely rigid laboratory pose. Operators watched for leaks and structural changes as the cycles accumulated. The process could reproduce thousands of flights in months, but not every part of service. Engine vibration, airflow, jet efflux, and the changing loads of takeoff and landing were absent or simplified. The court later warned that those omissions would tend to make laboratory life longer than service life. At about every 1,000 simulated flights, the pressure rose above normal working level for a proving test. Cycle after cycle, the cabin held. The aircraft had arrived with 1,230 service pressurizations and survived another 1,830 in the tank. During a proving cycle at a total of 3,060 pressurizations, water began escaping through a rupture at the forward escape hatch. Examination showed fatigue had existed for several cycles before the final spread. The shell had been carrying a growing crack while still completing the earlier pressure cycles. We opened at a forward escape hatch. We-IEP's evidence would point toward a rear ADF opening. Both were cutouts in the same basic pressure shell, where load had to flow around corners and through rows of fasteners. The tank result gave investigators a working fracture sequence and showed that several openings could carry severe local stress. Elba still needed its own physical origin, recovered from its own wreckage. Investigators estimated that the omitted service loads tended to make the tank test less severe than flight. One expert suggested the 3,060 combined cycles might correspond to roughly 2,500 service cycles. The court did not turn that estimate into a precise conversion because vibration and structural variation could not be reduced to one dependable factor. Even without a conversion, the contrast was unmistakable. A complete production cabin failed in a range that overlapped the service histories of the lost aircraft far earlier than the partial section result had led engineers to expect. The G-ALYP break redirected the Elba search. Investigators now knew what fatigue damage could look like after a pressure shell opened. Model drop tests helped predict where pieces from different breakup sequences would fall. Salvage teams returned to the mapped field and searched for roof structure that could test the new hypothesis. The failed cabin supplied a sequence rather than another cycle count. A local crack grew. The pressure shell opened. Surrounding structure unloaded, tore, and struck adjacent parts as other sections followed. Each step left different marks. Those marks could now be compared with metal recovered from the sea. By the end of August, roughly 70% of G-ALYP by empty weight or structure had been recovered. The figure included about 80% of the power plant and only part of the cabin and equipment. Large gaps remained. Engineers laid the available sections into their approximate positions and treated every torn edge as part of a sequence. A fracture caused by internal pressure should leave different deformation from a piece torn away after the cabin had already opened. Paint transferred between parts could show which surfaces struck during breakup. Distribution at sea could show which pieces separated early enough to drift or fall along a different path. The distribution and structural marks showed that the pressure cabin failed first near the front spar region. Model drops tested whether proposed sequences could reproduce where major pieces had fallen. Contact marks and paint transfers placed some components against others after the cabin began opening. The evidence did not support an engine separation or an external mid-air collision as the initiating event. It described a cabin burst while the aircraft had been flying substantially normally, allowing the investigation to move from the whole airplane toward a particular part of the pressure shell. A roof skin section containing 2 ADF aerial windows became the decisive physical evidence. The opening sat above the passenger cabin, where antenna equipment required brakes in the otherwise continuous shell. Investigators reconstructed fracture directions through the panel and found fatigue near a countersunk bolt hole at the starboard aft corner of the rear opening. That local damage, together with the wider breakup sequence, led the court to call the bolt hole area the most probable origin. It was physical evidence from G-ALYP, not a location borrowed from the water tank aircraft. Another corner of the panel contained a small manufacturing crack that had been stop drilled. Investigators examined it as a possible starting point and found no fatigue there. The countersunk bolt hole area carried the stronger evidence. From the surviving metal, the court could establish the rear ADF window region and name that hole as the most probable local origin. The first microscopic break remained beyond recovery. Strain gauge work on representative structure explained why an opening region was vulnerable. At normal cabin differential, investigators extrapolated about 43,000 pounds per square inch at an edge. Adding other known loads brought the estimate to roughly 45,700, around 70% of the material's ultimate strength. These were test-derived estimates of local stress, not readings taken from the recovered G-ALYP panel. They showed why a shell that looked comfortably strong in a gross pressure calculation could place one small construction detail under a severe repeated load. A stress below ultimate strength can still be dangerous when it repeats. Once a fatigue crack starts, its tip concentrates stress in the remaining material. Growth may be slow for many cycles, then accelerate as the crack lengthens and the intact section becomes smaller. The final cabin opening can be sudden, even though the damage developed over months. The inquiry tested other explanations. Weather did not account for the Elba loss. Investigator examined fuel venting, refueling damage, control failure, engines, and explosive possibilities. Some issues still deserved correction, but the alternatives did not fit the complete pattern as well as pressure cabin fatigue. The court found that fatigue caused G-ALYP's pressure cabin to fail in the rear ADF window region. That finding belonged to Elba and to the roof structure recovered there. It directed the engineering response toward pressure cycles, cutouts, fastener details, and local stress instead of the broad set of theories considered after the first loss. The new evidence returned investigators to the old partial cabin test. Before its long fatigue program, that specimen had received 2 applications at twice working pressure and nearly 20 more between working pressure and that maximum. A production aircraft also received a proving test around 133p, but it did not enter service with the same 2p preload history. The distinction was local and physical. Metal around these specimens' highest stress concentrations had already been driven beyond purely elastic behavior before the cycle counter used to demonstrate fatigue life began. Under an ordinary elastic load, metal returns close to its original shape when pressure is released. A sufficiently high local load can leave a small permanent deformation. That change redistributes part of the next load into nearby material and reduces the peak at the original hotspot. The specimen could therefore survive later working pressure cycles more easily at a detail that had yielded during the earlier 2p tests. The proof loading had not made the whole structure universally stronger. It had altered the exact local stress pattern the fatigue program was meant to measure. Loading history was only half the mismatch. The specimen was a forward section closed at its cut ends by stiff bulkheads. Those boundaries affected how pressure load traveled through the skin and frames. The rig did not include every opening, joint, and transition found along a complete production cabin, including the rear ADF region that later mattered on G-ALYP. A part of the structure could demonstrate the behavior of the details it contained. It could not reveal a stress concentration that was absent or loaded differently outside the rig. Cap 127 called preload at least a partial explanation for the anomaly between more than 16,000 later working pressure applications on the specimen and roughly 3,000 combined cycles at G-ALYP's failure. It did not supply a correction factor that converted one number into the other. Thickness varies, fastener holes and countersinks vary, joints carry load differently, and small manufacturing details change where a crack first forms. 2 cabins built to the same drawing can therefore reach fatigue failure at materially different lives. One specimen could no longer define the life of a fleet. The rig needed production geometry, a loading history that matched the aircraft, and enough margin for variation from one cabin to another. Static strength still had to be proved, but on a separate article from the one used to measure fatigue. The old section had produced a valid result for its own geometry and loading history. Airline service exposed everything that result left outside the rig. The court found no wrongful act, default, or negligence by a party or employee. G-ALYP had been maintained to its approved schedule and was airworthy so far as could reasonably then be known. De Havilland's approach matched what the court regarded as good engineering practice at the time. Accepted practice had produced a cabin with hidden fatigue vulnerability, which made the method itself part of the safety problem. The recommendations changed what future-proof had to contain. Complete pressure cabins were needed for repeated load testing, while separate articles would often carry static strength work. Designers needed detailed calculations around cutouts, tests of representative joints and panels, and far wider use of strain gauges to map stress instead of inferring it from gross survival. Test lives also needed enough margin for variation among cabins. The objective was not to find one average failure point. It was to keep the weakest plausible production aircraft inside a safe operating life. Revised British requirements in 1956 called for repeated loading of a complete pressure cabin that had not already been used for strength testing. That wording directly addressed both weaknesses exposed by the inquiry, incomplete geometry, and prior high loading. Research continued into crack growth, local fastener details, structural redundancy, inspection, and methods that later developed into damage tolerance practice. The changes took years and crossed many aircraft programs. Rounded openings became visually associated with the Comet lesson, but geometry alone was never the full certification response. The Comet itself did not vanish. Later versions were extensively redesigned with heavier structure, altered openings, and lower local stress. They returned to service in a market now moving quickly toward other jet airliners. The original Comet one could not return without modifications too extensive and costly for normal airline operation. The aircraft that had opened the jet age lost its commercial lead, but its investigation supplied physical evidence that every later pressure cabin program could use. The lesson traveled farther than the surviving fleet. Elba supplied enough wreckage for a positive finding. Naples remained in deep water. The similar phase of flight and the evidence that could be recovered made the fatigue explanation appear applicable to G-ALYP, but the court gave no definite cause. The two losses could inform each other without pretending that missing metal had been examined. The Comet pressure cabin brought high repeated loads into a structure with cutouts, fastener holes, and local stress peaks that varied from aircraft to aircraft. The old partial section survived 18,000 working pressure applications because its geometry and earlier loading made it a different object from the cabins in service. The number was accurate, the promise attached to it was too broad. After Elba and Naples, a new airliner would have to prove the life of the complete cabin it intended to fly.